Hello students, our next topic is examples of constraint forces. Here we will be dealing with some specific examples in which there is the involvement of constraints. The first one is wedge and block. So before that, what are constraints? Constraints are the restrictions or the limitation on the freedom of movement of particle or a system of particles. Constraints are the restrictions or limitations on the freedom of movement of particle or a system of particle. Okay, you can take some example. An ant moving on the surface of a sphere. Okay, when in that case, ant cannot leave the surface. Its motion is restricted to be only on the surface. So in that case, that is a constraint force. There is a constraint equation for this case, for the movement of ant on the surface of a sphere. And we can take another example, an oscillating pendulum. Here, the length is a constraint. Length is a fixed quantity and there is a relation between length and the parameters or the coordinates. So that in that case, that is the equation for constraint. So constraints are the restrictions or the limitation on the freedom of movement of a particle or a system of particles. Okay, our first case is wedge and block. In this case, here we have a wedge. Wedge is this triangular shaped thing, and here is a block. Wedge and a block. This block is sliding on this wedge. Also, this wedge is moving towards sliding on this surface. Okay, so a block slides on a wedge, a planar surface, which in turn slides on a horizontal table as shown in the sketch. So this block is moving downwards and this wedge, this triangular shaped wedge is moving along this horizontal direction. Now the angle of wedge is theta. This is the angle of wedge which is a constant, and h is the height of the wedge. H is the height of the wedge. Okay. Now we have to find out how are the accelerations of the block and the wedge related. Since the wedge is moving towards the right direction and the block is sliding on this wedge, there will be a relation between the acceleration of the block and the acceleration of the wedge. Now initially we take the position of block as the x coordinate as small x and the y coordinate as small y, and the initial position of the wedge, let it be capital X. So we have to find out the relation between the accelerations of the block and the wedge. Okay. Now because the wedge is in contact with the table, we have the trivial constraint that the vertical acceleration of the wedge is 0. Since this wedge is always in contact with this horizontal table, the acceleration in this direction or the vertical acceleration of the wedge is 0. That is a condition, that is a constraint. Okay, now to find the less obvious constraint that the block slides on the wedge, let x be the horizontal coordinate of the end of the wedge and let x and y be the horizontal and vertical coordinates of the block as shown. Okay, now we have to find a relation between x, y and x. Now look at this figure. Since this is the angle theta, what is this? The total height is h. So this distance is h minus y. And this distance is x. And so the total distance from the block is small x. And the distance up to the wedge is capital X. So this distance is x minus x. Okay. So from this is a triangle. From this, find out tan theta. So tan theta opposite side by adjacent side, that is h minus y by x minus x is equal to tan theta, or h minus y is equal to x minus x tan theta. Now we have to find out the acceleration among them. Okay, so we differentiate this equation twice with respect to time and rearranging. we obtain the equation as. So when we differentiate this first time, h is a constant, which is the height of the wedge, that is a constant. So h is 0 and we get minus y dot x dot minus x dot tan theta. And again differentiating, you get y double dot x double dot minus x double dot tan theta, and rearranging and cancelling this minus sign, you get the constraint equation. Y double dot is equal to x double dot minus x double dot tan theta. This is the constraint equation for the acceleration between acceleration of the block and that of wedge. Our second system, constraint system, second system is a pulley system. So we have two pulleys and the distances are shown. The first pulley is at a distance x and the second pulley is at a height h. And this is the position where we are giving a downward force. Okay. So the pulley system shown is used to hoist a block. Okay, we want to hoist this block and we are pulling it downwards. How does the acceleration of the end of the rope is related to the acceleration of the rope? So what is the relation between acceleration at the end of this rope and the acceleration of the block? What is the relation between acceleration of the end of the rope and the acceleration of the block? Now we can see from this equation, from the figure, what is the length of the rope? Length of the rope is starting from here, going through and up to here. So starts from here, it goes around this and also goes around the second pulley, and here it is. This is the end. Okay, let L be the total length of the rope. So that is equal to, this distance is x. Now this is the circular half circle. So its perimeter is pi r, where r is the radius of the pulley. So pi r. Then what is this distance? That is x minus h. H is this distance. So x minus h gives this length. Okay. So x minus h plus again pi r. 2 pi r is the whole circular perimeter. There is only half distance. So it is pi r plus x minus h. So this distance. So you get the equation for L is equal to x plus pi r plus x minus h plus pi r plus x minus h, where r is the radius of each pulley. Now on differentiating this equation twice, you get this 0 x double dot plus, this is a constant, that too is 0. Here too x double dot, h is a constant, that is 0. Then this term is constant, that becomes 0. Here x double dot minus 0. Hence you get the equation x double dot is the acceleration of the block. It is equal to minus 1 by 2 x double dot, or x double dot is the acceleration at the end of the rope. So the block accelerates half as fast as the hand and it is in the opposite direction. So twice x double dot is equal to minus x double dot, small x double dot. Okay, the block accelerates half as fast as hand in the opposite direction. Since it has a negative sign in the equation, the direction of block, the movement of block is in this direction, acceleration of the end of, at the end of the rope is in this direction. So they are opposite. So x double dot is equal to minus half x small x double dot. Okay.